Okay, welcome back. And this is the last talk. And it's by Cornelius Pillen from USA. We are number one. And proving and disproving conjecture about conflicts.
Thank you. Yeah, this is somewhat of a sentimental journey for me, and some of that will be together with Dan and Chris and Paul, but I won't cry, so it's okay. All right, but before I start, this is the last talk, and I think we should really thank the organizers. And I hope there are probably some names that I forgot here, but organizing a conference is a lot of work. But it is a very important service to the community. And I'm very grateful that they did this conference. It's been a very nice conference. And for the younger people, I just hope that one day you will also be organizing conferences for the younger people. Okay, so maybe we should give them a hand. Yeah, I thought I'd do this at the beginning of the talk before people fall asleep. Okay. Also, happy birthday, Danny. I want to sing. Okay. All right. So the story here starts with a bulletin paper from 1973, a very short 2-page paper by Jim Humphreys and Verma, communicated with George Seligman. And in that paper, I will tell you what's in the paper in a second. Let me just do the obligatory background. So, what are we talking about? We're talking about algebraic groups, and I'm going to be simple. They're very similar to Paul. I'm going to say make everything simple, semi-simple, even so some reductive stuff will show up throughout the talk. And we're looking at rational representations of algebraic groups, and just think SLN. It's enough. And then there's the usual Lie algebra or Lie theory that comes with it. So I have a maximal torus, I have a Borel subgroup that give me a root system. I'm going to use S for the simple roots. Then alpha 0 will show up a couple of times. That kind of is something that helps us measure the size of weights. So that's the maximal of the short roots. Rho is the half sum of the positive roots. H, the Coxeter number of the root system. W, the ordinary while group. And W0 will be the longest word for while. So algebraic groups come with 2 more families. And one of them are the Frobenius kernels, which I will denote by G sub R. And the other ones are the finite groups of Lie type. And their representation theory is very much intertwined. Okay, so the Frobenius kernels are the kernels of the Frobenius morphism, and the finite groups are the fixed points of the Frobenius morphism. Okay, so everything here is over an algebraically closed field of positive characteristic P, and Q is the R power of P. So Humphreys and Verma were very much interested in how these 3 things are intertwined. In particular, their goal was also to say something about the finite Chevalier groups. So I need some more notation, characters and weights. We need those to label all the representations that will show up here. So I will use the letter X for the characters of the torus. So this is just Z to the power of the rank of the group. I will use X sub plus to indicate the dominant weights. And again, I don't know where this started, but 0 became a natural number at some point. So 0 is included in N. X sub R will be the PR restricted weight, so all the components are at most PR minus 1, and I will work with X1 a lot later on. Rho, if you write it as the sum of fundamental weights, is simply 1, 1, 1, 1, 1. And we usually label, you will see all the modules that will show up here will be labeled by some kind of highest weight. Okay. All right, so let's start with the simple modules. These are denoted by L of lambda, where lambda is one of the weights. And thinking back of the triangle, Curtis showed that if we have the simple representations for the Frobenius kernels, then they can be lifted to the algebraic group. And on the other hand, if I take simple modules of the algebraic group in the PR restricted region, then they give me a complete list of the irreducible representations for the Frobenius kernels. And Steinberg also showed that in a similar way, we can get the simple objects for the finite group. And in here comes, of course, Steinberg's tensor product theorem that Paul already mentioned before. And so even so, there are infinitely many simple objects for the algebraic group. It is really, if you understand the finite set of p-restricted weights, then you can get the characters of all the weights. And so on the simple level, there's a very nice way how this triangle kind of works together. The upper m and the upper one or the upper integer inside some brackets will be always the Frobenius twist. Right? All right, so now Verma and Humphreys, they wanted to look at the principal indecomposable modules or the projective covers or injective hulls of these simple modules. And they noticed very early on, some other people had worked on that already, that those objects for the Frobenius kernel are very similar. There's a very close relationship to those for the finite. And so what Humphreys and Verma were advocating in that paper was that I take the injective hull or projective cover of a simple module in the Frobenius kernel, I lift it up to the algebraic group, and then I reduce it down to the finite group. And they notice that in many cases, that thing, first of all, what happens is that thing remains projective and injective for the finite group. In many cases, it even remains indecomposable. And in some cases, it decomposes. So that was kind of the idea of that paper, that 73 paper. Okay. Now, there's no direct way to go without passing the algebraic group. And a few years later, Jaskowski and Jantzen independently actually found a way to go from the left to the right, but only at the character level, by finding a formula how you can describe the characters of the principal indecomposables for the finite group in form of those for the Frobenius kernels. But anyway, that's where this lifting came in. And yeah, all right. So let me also say specifically what they had in mind, how they wanted to do this lifting. And Paul already mentioned his favorite module, the Steinberg module. Okay, so if we take the Steinberg module, which has component p-1, I just take the first Steinberg module. That module is injective and projective for the Frobenius kernel as well as for the finite group. Okay, and so what we're going to, I'm sorry, yeah, I do the line by line thing because I like to surprise myself. Next. So the idea that they were looking at is if you take the Steinberg module and you tensor it, because the Steinberg module is injective and projective, and you tensor it with something, you get injectives and projectives again. And so they were tensoring it with an appropriate simple module. You will see that lambda tilde are showing up a few times. That's just the right cousin that we have to use. It is another restricted weight. And so they were looking at these tensor products, and these tensor products are injective and projective, and so they decompose. And so the injective hull of the L of lambda appears exactly once. And if you do the standard trick by throwing in the torus to keep track of the weights, then you can actually say that they appear exactly once as the G1T summand that has the highest weight, which in this case would be twice the Steinberg weight plus the omega 0 of lambda. Okay. And so so basically what happens is on the G1T level, we know that that tensor product kind of decomposes into Q1 of lambda plus some other Qs. And in red, I put it on the finite group level. That's exactly the same story. And of course, since the Steinberg module and the simple ones can lift it, there is a nice way how we can go around the triangle to do that. And so these sometimes called Humphreys-Verma question or Humphreys-Verma conjecture. Actually, if you look at the paper, it should be the Humphreys-Verma theorem. They promise a forthcoming proof. But is the question whether you can lift these Q's from the Frobenius kernel to the algebraic. And I'm going to leave the finite groups pretty much out from now on. That's what I will concentrate on in this talk. Okay, so let me do also one very explicit example. Let's take P equals 3. Let's take the group just to be SL2. If you look at the restricted enveloping algebra, in that case, that's a 27-dimensional algebra. And of course, we know that this is equivalent to representations for the first Frobenius kernel. The weights are just integers, and there are 3 simple modules: the trivial module, the natural representation, and Steinberg module. And if we do this Humphreys-Verma construction and we take the Steinberg and tensor them with all the available simple ones, then on the left side, you will see, of course, first we get just the Steinberg. The Steinberg tensor, the natural representation that remains indecomposable, and that's the lift of that's the injective hull of L of 1. And you can see if we do Steinberg tensor Steinberg, that one of the Steinbergs will kind of split off, and you get the Q1 of 0. If you do the same thing on the right side for the finite group has 24 elements, right? Then you can see that the Q1 of 0, which can actually be lifted and lifts over there, actually decomposes into a U1 plus another copy of the Steinberg. So this is kind of typical what happens. But anyway, the Humphreys-Verma conjecture is true for SL2 and P equals 3. All right. So some, I don't know, 10 years later, roughly, first Ballard and then Jantzen, they found a very beautiful proof for this positive answer to Humphreys-Verma question in what Jantzen called the p-bounded category. So he took the category of G modules whose highest weight satisfy this inequality. So you're basically cutting off at twice the Steinberg weight because you want all those tensor products of Steinberg tensor, a simple module, to be inside the category. Okay, and this category that today we do this many, many times. This category has injectives and projectives. And first of all, there's one observation. If the prime is large enough, then H is the Coxeter number, right? H is the Coxeter number, yeah. So if the prime is large enough, then this tensor product Steinberg with any simple module is both projective and injective in this p-bounded category. Okay, and here's already a first warning. This characterization fails miserably if the primes are small. Okay, that is definitely not true. But then again, here is one reason why we like that lambda tilde, because the lambda tilde is just the right one, where the multiplicity of L of lambda in the socle is exactly 1. And so what happens is that we get the injective hull of L of lambda in this p-bounded category showing up exactly once as a summand. And it's also not too hard to show that this will also have a simple socle, even as a G1T module. And so the answer that Ballard and Jantzen found is that the Q1s can be lifted, but they can be lifted uniquely, and they're exactly the injectives and projectives in this particular p-bounded category. So this is a very nice answer that they found. All right, so moving on, I need to introduce more modules. We saw many of them already this week and this morning in particular. So the nabla will be the induced module. I take a one-dimensional B module affording the weight lambda, and I induce it up to the algebraic group. Also in the modern language, I guess people call those the co-standard ones. Then we have the simple module shows up as the unique smallest submodule inside them. kind of have a dual, the Weil module or highest weight modules. And there's a very nice X between them, namely all the X vanish for I being greater than 0. Okay. And well, since we're doing characteristic P where things are not semi-simple, what's the best thing to direct sums are filtrations. And so most people will know here, we will say that a module, all my modules here are more or less finite dimensional, will have a good filtration if it has a filtration where all the factors are these induced modules. Okay. And again, there's a very nice X cohomological criteria to decide when a module has a good filtration. Okay, now if the module has a good filtration and its dual also has a good filtration, then we call those things tilting modules, or equivalently, modules that have both a good filtration and a filtration by Weil modules are called tilting modules. Okay. And then Paul already mentioned it this morning. There's a theorem that's due to Donkin and Ringel that said for every dominant weight, there exists a unique indecomposable tilting module labeled with that highest. And also very important here is something that there is a theorem that's due to various versions, one Donkin and finally Mathieu. I hope I spelled the name right. Maybe not. Okay. Too many T's. Yeah, I'm sorry. So it says that if you have two modules that afford a good filtration, then the tensor product also affords a good filtration, which of course also implies that the tensor product of tilting modules are tilting. Right. Okay. So let's go back. Well, let's go forward. I don't know. I want to talk about Donkin's so-called tilting module conjecture. So let's go back to what I talked about earlier in the Humphreys-Verma setup. So we had the Steinberg, we tensored it with that simple module, and we got the Q1 exactly once and some other stuff. And this is one of those kind of strange coincidences in life. When I was a graduate student, Donkin actually came to visit UMass for a week, and I didn't know anything about tilting modules. I didn't know what they were, but I was playing around with tensor products. And, you know, we talked a little bit, and he started asking me this question, and I had this cute little trick where I could actually show, if you take the Steinberg module and tensor it with a simple module, that the summand that has the highest weight will be a tilting module. Now, this tensor product, Steinberg tensor, a simple one, will show up later quite a bit, and we don't know whether the whole tensor product is a tilting module. But it's kind of surprising that the worst one, in some sense, the one with the highest weight, is a tilting module. And so you can also see, if you go back to Jantzen's argument, Jantzen already proved Donkin's conjecture 10 years before Donkin's conjecture was formulated, because in that p-bounded category, these tensor products are tilting. And so therefore they have good filtrations. And since the injectives are projectives, they have Weil filtrations. And so we get that these are actually tilting modules. And so Donkin then conjectured that this should be true in general, not just for the large problems. And that's what we usually call the tilting module conjecture, going back to Donkin, which is incidentally I first heard about it at that, we saw the picture now many, many times at that conference in 1990 at MSRI. Okay. All right. Yeah, due to popular demand, I brought my Lego picture again. So here's Bob the builder and Rhonda the representation theorist. Okay, so I mean, Paul talked about this morning. Of course, the big questions are, at this point, find reasonable ways to find what the simple modules look like, right? And then, of course, also, how can you stick the simple modules together, which is cohomology, and the two questions are intertwined. So this is kind of the picture that I use if I want to explain what I do to my children. And so when my oldest son was young, somebody asked me, what does your dad do? And he said, well, He rides the elevator and he plays on the computer. But anyway, Paul talked about this morning. So when I was a graduate student, the Holy Grail was proving Lustig's conjecture, but we now know that yes, there's much more dependence on the primes than we originally thought. And so these days, I guess all the people that do geometric representation theory, they prefer the tilting modules over the simple modules. And so we're going kind of like that route to find reasonable formulas for the simple modules. So this is why people are interested in the tilting modules. And what would happen is if Donkin's conjecture would be true, then that would be a very cheap way that Paul talked about this morning. That would be a very cheap way to get the characters of the simple modules from the characters of the tilting. It's using Humphreys reciprocity. All right, so Paul already mentioned this morning P filtrations. So I have to introduce one more type of filtrations, and I'm going to just stick with P filtrations. Almost everything I do for P, you can do for P to the R, but for simplicity of the exposition, I just want to stick with that. So we say that the module has a P filtration if it has a filtration where the factors of the form you have a simple module, a simple restricted module tensored with an induced module of arbitrary dominant weight once twisted. Okay, so Paul mentioned that if you do quantum groups, this is completely boring because that's always the case. But in characteristic P, this is something that is very nice. Well, I don't know if it's nice, it's very complicated. Okay, and one of the downsides of this is up to this point, nobody has found any kind of nice cohomological criterion to say when a module has such a filtration. And this makes it quite difficult. And I should also say that this goes back to a question that was posed by Jantzen, because he was asking if I take one of these induced modules, do they actually have a P filtration? And he noticed that if the weights are very small or if the weight's in some kind of generic position, then that's always the case. But in general, that was something that the answer is still open. Let me just mention that Partial and Scott in 2015, they have a positive answer to that question. But again, the prime has to be 2h minus 2, and they assume that Lustig's conjecture holds. And Anderson proved it in general, but you can see the prime has to be of the order of h squared here. So again, for the small primes, this is a completely open situation. Okay, so at the same 1990 conference at MSRI, Donkin had a second conjecture, and the conjecture, yeah. So he said, okay, let's take a finite dimensional module M, and he said, okay, so this module M should have a P filtration if and only if M tensored with the Steinberg module has a good filtration. Okay. And I will refer to this as the Donkin's filtration conjecture. Okay, so let me say, no, I shouldn't say okay too often. That's a German thing. Okay, right. A few words about, I don't know what Donkin's motivation was, but here just a few things. Paul already mentioned the theorem of Anderson and Abush. If I take the Steinberg module and I tensor it with a twisted induced module, that's again another induced module. Then these Steinberg module tensor restricted simple modules, if we could say that they are tilting, that is equivalent to the left to right part of Donkin's filtration conjecture. So you can reduce it down to that case, and you can see how how these tensor products become very important. We also know that if P is bigger than 2h minus 2, then the left-right direction of this conjecture does definitely hold. And the right-left direction would give a positive answer to Janssen's question, because obviously if I have an induced module that tensored with Steinberg that has a good filtration, due to Mathieu. And so therefore it should have a p-filtration. Okay. And of course, in a roundabout way, this conjecture would also give kind of a cohomological criteria for modules having a p-filtration. Okay, so this is kind of like, yeah. All right. So Donkin made these two conjectures, and obviously, I'm pretty sure he thought they had something to do with each other. But it took actually 28 years to show that one conjecture implies the other. And this is work by Kildetoff Nakano and Paul Sabaji, who finally, the last piece I think was not in until 2018, who basically showed the following. If we take the Steinberg tensor with a restricted simple module, if those guys are tilting and a certain set of modules, induced modules have good p-filtrations, then Donkin's tilting module conjecture will hold. Okay, so that basically is what it says is that Donkin's filtration conjecture implies the tilting module conjecture. Okay, but it took quite a while to get there. So let me give you like a little bit of a picture here. So the toughest one is the filtration conjecture in both directions, which would give which implies the positive answer to Janssen's question, and of course the left-right direction. Now I call that the finite Janssen question. I call that because for a fixed group, there's a finite set of modules for which we need the fact that they have a p-filtration. So I call that the finite Janssen question. That's what we need to get the tilting module conjecture. The tilting module conjecture does imply the left-right direction of the filtration conjecture, and of course it implies the Humphreys conjecture. Okay, so that's kind of how these things are interrelated. Yeah. So then a few years ago, Dan suddenly suggested we should look at Donkin's tilting module conjecture again. And my first reaction was remembering this Gary Larson cartoon, the little frog picking a big project. Okay. My first reaction was, come on, Dan, nobody in 30-something years has gotten anything out of that. You know, why should we do that? But then we were tenured, so who cares, right? So anyway, it also, yeah. So then I should also go back to where Jim Humphreys was my advisor, and whenever I thought I had some kind of idea or something like that, and I would go to him, then he would also look at me and he would say, "But is it true for G2?" And then he would giggle. Yeah. So. Well, there's some prophecy because we started looking, we started out trying to prove Donkin's conjecture for the rank 2 groups, which at the time only type A2 was actually known, and we tried to prove it. I mean, for each group, there's only a few primes, right, that you need to look at. And we tried to prove it, and I think we thought we had a proof for p equals 2, and then we played around with Steve Doty's gap program, which seemed to produce some really odd answers. And then it was clear to us that either Doty was wrong or Donkin was wrong. And we sat down and we could actually show that it is wrong. So that we found a counterexample. And let me, this will get the next 5 minutes will be kind of a little bit technical. So, but let me show you how we kind of found a bunch of counterexamples, at least in kind of low ranks. So let's assume for a second that the tilting module conjecture holds. So the Q's are tilting modules. Then we know that if I look at the G1 homomorphisms between two of these guys and I untwist them, then they have a G module structure and they have to be tilting. I think this is first in the Kildetoff Nakano paper, I believe. Yeah, so they have to be tilting. the advantage of working with those, they're much smaller tilting modules than the Qs itself, okay? Now, that's obviously from general nonsense that if you looked at the G1 extensions between two simple modules, that embeds in this harm, okay, of the Qs. And so if you would find some kind of simple module that embeds in the X1 for the Frobenius kernel, then this simple module would have to appear in the socle of a tilting module, which means it has to appear in the socle of some while module. And because the weights are not too big, this is actually something you can really get your hands on, okay? So today is what, Friday? So let's do D4, okay? Let's do D4. So let's do D4 and P equals 2. I'm going to denote the fundamental weights by omega 1, omega 2, up to omega 4. Omega 2 is the one that is not minuscule. It's the one that corresponds to the root at the center. Okay, then there's a very nice paper by Peter Sin and his student Dowd, where they calculated a lot of data about X groups for characteristic 2. Up to rank 4, I think they pretty much calculate everything. And here's one example for type D4. If you look at the cohomology of the simple module L omega 1 plus omega 3 plus omega 4, they calculated this. And what's interesting here is that the L of omega 2 is not an induced module. So this is a simple, it's not induced. And so this cohomology group this cohomology is not a tilting module. If you untwist it, it's neither does it have a good filtration, nor is it a tilting module. So if the tilting module conjecture would hold, then we would have to be able to embed L of omega 2 in this harm group that you see there in the second line. Okay. But you know, it's not too hard to calculate the weights, and so we would need we can calculate the highest weight of that harm group. Okay, and please note that this is not untwisted, so this is the actual weights. So what would happen is that we would need this omega 2 to show up in the while module with highest weight gamma. And gamma has to be linked to omega 2 and has to be between those two weights. There's a finite list, and even so, it's dirty work, but you can easily prove that that just doesn't happen. So it does not appear in the socle of any of those things. And so therefore, the tilting module conjecture can also not hold for type D4 and P equals 2. So anyway, you know, doing this kind of stuff, we found several other low rank examples, type B3, P equals 2, C3, P equals 3. So we found some more. And then also notice that in all of these cases, that there was some strange behavior by the cohomology for the Frobenius kernel. So this is something that we noticed there. Now, I think Donkin already was looking at kind of, you know, reducing things down to Levy subgroups. And I think he was hoping to maybe be able to prove the tilting module conjecture by reducing down to Levy subgroups. It turns out that that will not work. But of course, it's very good to produce counterexamples. So, I mean, the thing is, if the tilting module conjecture holds for some group G, then it would also have to hold for any Levy subgroup. And the same is true for the P filtration business. So if we know that a certain module has a good P filtration, and we look at the corresponding module that corresponds to the Levy subgroup, then that would also have to have a P filtration. And so, of course, we can use the contrapositive of these two theorems and our finite set of counterexamples, and we are able to produce counterexamples for any root system except type A and E2. Okay, and in type E2, we know that Donkin is true, and type A is still completely open. Okay. All right. So let me maybe collect the positive results first. So this is kind of the 1980s standard. So here we have to assume that we are assuming that the prime is at least 2h minus 2. In that case, Jantzen's work shows that Donkin's tilting module conjecture holds, which implies, of course, Humphreys and Verma. And we also know that the Steinberg tensor, any simple module in the restricted region, is a tilting module. So the latest thing is now, I think Dan already mentioned it during Eric's talk, we were able to push it down from 2h minus 2 to 2h minus 4, which is maybe not much, but anyway, it's the first time in 40 years that there's some kind of general statement. The first three statements are the same, and you notice here I threw in this X business because it turns out if you look at those, that these X groups will always be, basically, they will all the weights will always be pushed into the lowest alcove, and so trivially they will all be like tilting modules. Okay. Yeah, let's also look at the rank 2 cases. So for the rank 2 cases, Donkin is true if and only if we are not in type G2 and P is equal to 2. Okay, otherwise it will always true. And also, again, this strange relation with the X1, the only time you get something that's not a tilting module is that G2 and P equals 2 situation. Otherwise, those things are always kind of nice behaving. Okay. All right. So let me say a few words about methods and techniques that you can use here. So the first thing is you can look at Jantzen's idea with these kind of truncated categories and injectives and projectives, and then you can push it a little bit further depending on the weights, depending on the root system. You can get a little bit stronger statement out of that. The second ingredient is the reduction to Levy that allows you also to rule out many cases. The third one is that we need that this finite set here of induced modules has a good p-filtration. And that is really the unpleasant part. This is really, really the hard part. Okay. For example, this generic statement that we got to go from 2h minus 2 to 2h minus 4, that more or less just uses the first two techniques. Okay, you don't really need to use you don't really have to look at p-filtrations. Okay, but the p-filtration business, that really, that is really nasty. So let me give you a couple of examples. The first example, let's take A4 and p equals 2. If you use the strong linkage principle and the first two techniques, then you can basically show that the tilting module conjecture will hold, and you can reduce everything down to one single module having a two filtration, and that is quite doable. You can actually argue that so you can do type A4 and p equals 2. Now, this is kind of an unusual example. The better example here would be to look at G2 and P equals 7. Now, that's an interesting example because 7 is bigger than h, but less than 2h minus 4. Okay. Now, what do we know in that case? Well, first of all, we know that Lustig's conjecture, or we're doing the G1T version of Lustig's conjecture, holds in that case. Okay. There are also Anderson and Kaneda have a paper from 1989 where they give explicit formulas that allow the computation of the G1T radical filtration of these. These are the co-standard modules. The Z1s are the co-standard modules for the Frobenius kernels. Okay, that Paul mentioned them this morning also. And these formulas are given in terms of the inverse Kashtan-Lustig polynomials. And these were calculated by Lustig in his paper in 1980. And so what we can do is we look at the induced module, but we kind of look at the induced module first by going from the Borel subgroup to G1b. So we're looking at the Z's first and then inducing from G1b up to the group. Okay. And so, you take one of these co-standard modules for the Frobenius kernel, and you take a filtration of simple modules, and then will all be of the form L of mu I, where mu I is a p restricted weight, times p plus tensor p times some other weight. Okay, some other weight. And so you can't now, if you would just be able to induce each of those factors, then we would be in good shape, right? But the problem is that, yeah, induction is only left exact, so there are the right derived functors, and so there could be cancellations. And so you really need to look at these filtrations, and you have to make sure that certain things don't happen. So if I is less than J, if something appears first in the filtration, then you need to make sure that the homomorphisms from the induced module from the sigma I into the right derived functor of the sigma J, that is either zero or an isomorphism. And if that is true, then you can't have any cancellations, and you get that you have a good filtration. So it's quite tricky to do that. Okay. And here's just one of the 16 alcoves, the 129 composition factors. But there seemed to be some magic happening. The way they appear in the layers is that these things don't happen. Okay, but that shows you a little bit that there's some work involved in getting these things. I don't know if this impresses you. If you want to impress me, I don't know why you would want to do this, but do this for A4 and P equals 5. I would very much love to see that. Okay, but that's, yeah, because that's another case where 5 is between H and 2H minus 4. All right. There's a little bit more, I call it bad news, because there's something else that kind of goes against my intuition. There's a third conjecture by Donkin. It's actually the oldest one that he made at the Arcata Summer Institute in 1986. And in that conjecture, he was saying that given a G module V that has a good filtration, then the nth cohomology of we could just put G1 in there, of the Frobenius kernel, untwisted, should again have a good filtration. That was the conjecture he made. And unfortunately, van der Kahlen found the counterexample. And in particular, what he found he constructed a G module that has a good filtration, but whose G1P socle does not have a P filtration. Okay, so that basically means like if Donkin's filtration conjecture holds, we cannot expect that these P filtrations somehow respect the G1T socle layers or radical layers, which is something that obviously is not, yeah. It definitely went against my intuition somehow. So this is obviously a very difficult problem. So let me spend the last couple of minutes talking about another approach that we've looked at. So for type A, it's open. We don't know. We haven't found any counterexamples for type A. We know it's true up to A3. A4, I think we still need P equals 3 and P equals 5. Yeah, okay. But so well, with type A, of course, you have a lot of more machinery available. So we were looking at Schur algebras. So sigma D will be the symmetric group on D letters, and V is the natural representation of GLN. Then we know that the category of S and D modules is equivalent to the category of polynomial representations of GLN, which then gives us information about SLN. And I will switch now a little bit. Instead of using weights, I will use partitions, but we can label the same kind of objects, the simple things, the while modules, the co-standard modules, and also tilting modules. We can label them not with weights now, but we will label them with partitions. Okay. And there are various Schur type functors. So let M be an integer greater than or equal to n, then there exists an idempotent that helps me go from the larger Schur algebra SMD to the smaller Schur algebra SMD, and it gives us a functor that sends SMD modules to SND modules. And if you want to look at algebraic groups, this is very much compatible with reduction to a Levy subgroup. So that's very much kind of how it behaves. But this also has this functor also has a right adjoint, which goes from SND modules to SMD modules. Okay, and this inverse functor is a right inverse to the original one. So if we first do G and then F, then we get the original back. And the other facts, various facts about these functors is it sends co-standard modules to co-standard modules. And I'm going to put the bar on the nabla if I'm talking about if I look at it as an SMD module. So this is the same partition, but this time the co-standard module for the larger Schur algebra. Okay. Now, if you look at simple modules, it's a little bit more complicated what this functor GNM does to simple modules. And one way to characterize it, you can say it's the largest submodule of the SMD module nabla bar of lambda, whose composition factors, other than mu itself, are partitions with more than n parts. I mean, this comes simply from the fact that the inverse thing kills everything again. Yeah. So here is, okay, yeah, there's one more ingredient that I need. Hammer talked about this. David Hammer talked about this yesterday. The Moulineau correspondence actually come in. So giving a simple module for the symmetric group, we tensor with the sign representations, we get another simple modules. And the partition corresponding to this module is given by the Moulineau map. And so the Moulineau map is an involution on the set of p-regular partitions of D. The word p-regular here is for symmetric group people, not for algebraic group people. Okay. And so our goal is to understand the socle of certain tilting modules for S and D. And if n is large, if n is greater than or equal to D, then we know from Cohen, and Donkin that the Weil modules will have a simple socle, and that simple socle, the weight of that simple socle is given by the conjugate of the Moulineau map. Okay, so that's how this all goes in. Now the problem for us is n greater than or equal to D is useless to us. We really need to look at cases where n is smaller than D. So we need to look at that. And so here's one theorem that we have. We can basically say that the Donkin's tilting module conjecture will hold for type A if the multiplicities, the multiplicity of this, again, I put a bar over it when I'm thinking about it as an SMD module. So if the multiplicity of this L Moulineau of lambda bar, remember lambda bar was Steinberg plus a restricted weight. Okay. If this is 0 for any sigma other than lambda where it is equal to 1. This has to do with the fact that if the tilting module conjecture holds, then it will have a simple socle as a G module and as a G1T module. So this is one way. This is an equivalent statement, and just a few facts here. How far do you have to go? Well, it turns out M is at most 2 times N. Okay, so I mean you don't have to go all the way up to D to get these kind of things. And in the worst case, when lambda is equal to 0, so this would be about looking at the injective hull of the trivial module, which is always the worst case. That's actually when you get a partition of length 2n. It's an interesting partition that's actually self-dual or self-conjugate, I guess you say. Okay, so that's the worst case. And there's another cute little thing. If you look at the other extreme case, if you make lambda equal to p minus 1 rho, then it's not a fixed point, but it's a fixed point for Moulineau conjugate. And as a consequence of that, this has a consequence as for SLN, the so-called partial tilting module. So take a module that has like p-1 in the first n spots and then all zeros. These modules are actually simple modules in type A. And from calculations that I have done for other groups, this seems to be very unique for type A. This doesn't happen in the other types. So these are just two things that I want to say here. So let me finish. I have to finish. I was wondering because we have to stand here because of the camera, or they put a trap door here that just goes up and you go over time. But anyway, if you go back to that example of type A, 4 and p equals to 2, and you use this technique and some other arguments, then the tilting module conjecture boils down to simply finding the multiplicity of this simple module in this induced module. Okay, and the bad news is that induced module has dimension 5,717,000. So I don't know. Maybe Frank Lübeck can do it, but that's yeah. Anyway, let me stop taking your attention here. Thank you. Oh, right. Okay, I stopped already.
Any questions, comments?
You mentioned this counterexample by when did that appear?
I have it in my I have it in my backpack. I can show it. In the 80s sometime.
Oh, in the 80s.
I think, but early I have it.
Just a comment, I have a lot of data and bizarre behavior about the model and that I'm doing things like model p times p-1 row, lambda, things like that. Steinberg tensor product and results, which I thought would never have any interpretation. Maybe we should talk about it.
Yeah.
G2 and 5 is false.
Sorry?
G2 and 5 is false.
No, it's true. It's only G2 and P is true. For 5,
I see.
yeah, for 5 they're kind of lucky. The extension of the trivial module, the next module is very large. And for the G2P and 3, you can use this semi-repeated map.
So 3 also is true. So what is the false?
Yeah, only.
So for the bottom, you already provide actually the QH minus 3, the only. Right? I mean,
Yeah.
QH minus 4 is only 8 to equals 2, and that was not.
Yeah. It's only, I mean, it's all QH minus 3.
I guess the point is that what kind of argument we use, hopefully that we use on the argument. We will move forward. Any other questions? Okay.
So, in general, we may disagree. So we think that maybe we go down.
Yeah, unfortunately, I finished before my last slide, yes. I mean, so what's open is type A is completely open, and then of course, there is some hope, maybe for p greater than h or greater than e. Because our counterexamples, so far we only found counterexamples for primes 2. I think there are counterexamples for arbitrary large primes, but they will be for, the rank will grow as we know. But I haven't found.
Okay, now, can you go through this reduced model with the path mating definition?
This one?
Yes, and for that, has to be the dimension of the reduced model in this.
Well, I mean, Frank Lübeck on his webpage, he does a lot, but not all of them. I think you can probably figure it out with the Janssen filtration. I don't know, because the prime is 2, right? But maybe just sending an email to Frank might be. But yeah, I mean, he has, he has methods to calculate. I think this can be calculated. I tried with various tricks to get an answer before I got here, but I couldn't quite finish it off. So
my gap program.
I think your gap by 5,000,007. I don't know.
I think it should be.
It's too large. It's too large. Yeah, but I tried.
Okay. Well, maybe if we put it on the system.
Yeah, that's the other thing. Yeah. No, I mean, I'm pretty sure. Yeah.
But maybe nowadays it's a small argument.
Anyway, two more philosophy things here. We need more examples, and we need also people to write nice programs we can calculate. This is really.
And the point is that through these examples, look for patterns. What is the practice? Character formula, for example. Right. Any other questions or comments? I think it's not, and let's thank Cornelius Pillen